Welcome, everybody. It's my pleasure to introduce Mateus Juda, who will be telling us today about unsupervised features learning for sampled vector fields. Thanks, Mateus.
Thank you, Henry, for the introduction. Thank you for the opportunity to be here, and thank you all of you to join us. So our motivation is to talk about data-driven dynamical systems. So what we understand by that. So we understand by that just a bunch of points with vectors attached at each point. So here on the picture you can see a simulated van der Pol oscillator, and at some points on the plane we sampled the vector field and we just plotted the arrows. So that will be just our data, nothing more. So we do not know anything about the system which generates the data. We only know the data itself. So what we can observe here from this very simple example, we can observe that there is some kind of oscillation. So just to make sure, do you see my cursor, my pointer?
Yes, we can see it.
Okay, so we can observe that there is some kind of oscillation on the area on which I'm moving the pointer, and the oscillation is repelling. So it means that we are jumping out of the periodic orbit, either out of the picture or into the center of that picture. So it means that also in the middle there is a critical point, an attractor. And we would like to have a tool, first of all, a tool which will tell us that the data actually consists such oscillation and such attractor. So the data may be even much smaller, like on this picture, or much bigger and much more complicated, like on this one. And actually, this one is very interesting because this is a real measurement. The data is taken from a telescope which observed the surface of Sun. And what the telescope is giving us is a magnetic vector field on the surface of the Sun. However, the vector field is three-dimensional, so we have three-dimensional vector field, but the measurement is given only on the surface of the Sun. So we have three-dimensional vectors on two-dimensional plane. So in that kind of data, we cannot assume that the vector field is generated by any dynamical system. However, we would like to have the ability of the tool to also analyze this kind of data. So we do not assume that the data is actually given by a dynamical system. It is just a bunch of arrows, and we would like to analyze this bunch of arrows. So what kind of methods we can design and apply to this kind of data sets? So we are going to use topological approach. So first of all, we need to create some topological space for the data. And in that presentation, the topological spaces will be quite simple. Those are just two-dimensional simplicial complexes, triangulation of the plane, and the triangulation is taken on the points where the vectors are attached. So in this particular example, we just took the points and created the Lonay triangulation of that point cloud. And what we have as our input for later is the simplicial complex, and at each vertex of the simplicial complex, we have also the vector from the input data. Okay, so what can we get from our tool? I do not want to tell you now how we are doing that. I would like to show you first of all some results. So the tool which we have can actually recover from the van der Pol oscillator that there is actually the periodic orbit, the purple set, and there is actually the attractor in the middle, the green set. So how do we know that the green set and the purple set are repelling or attracting? So if you take a closer look at the picture, you may notice that actually the purple set is open. So there is no point, no edge on the boundary, either inner or outer set of the purple set. And the green set has all these points and all these edges on the boundary of the green set. So this thing can tell us that actually the flow is going out of the purple set and is going into the green set. So topologically, we have the property of being closed or open, and in terms of dynamics, we know that the set is either attracting or repelling. Okay, so that was quite simple example, and more complicated things may happen in 3D. So in that particular example, you can see the Lorentz attractor. So we took a three-dimensional space, the point on in three dimensions, and at each point of the space, we simulated the Lorentz system, and we ran the tool, and what we get from the tool is the upper approximation of the Lorentz attractor. Okay, so that's validate that the tool is working for 2D and 3D examples, not so small and not so easy to compute, and we would like to do something more with that. But before we say more about the tool and what we actually want to achieve, I would like to give you some brief introduction of the whole machinery which we use here. And I will do it on a very simple example. So we have just 4 points, and at the 4 points we have vectors attached. So the left-hand side picture is our input data. And as I said, we need to have some topological space. So in this particular example, we have just the very simple triangulation made of those 2 triangles. So we have 2 triangles, 4 vertices, and we have 5 edges. And how now we can interpret the input data in terms of this triangulation. So let's look at the point at vertex P. So we have the vector there, which is actually very close to the edge. So in some sense, we can right now interpolate the vector field in terms of the simplicial complex, in the sense that from the vertex P, because the vector from P is very close to the edge, we say that in this particular example, we are going from P to the edge PR. The same thing happened in vertex R. So from R, we are going to the edge QR, and from vertex Q, we are going to edge PQ. So here we can observe that there is a very small oscillation made of these 3 vertices and 3 edges. And the oscillation is right now on the simplicial complex. So we can think about that from the data, we extended the vector field into the simplicial complex. And what will happen in vertex S? So right now the vector is not pointing directly into the edge, not pointing directly into the RS edge or QS edge. It's pointing more or less into the interior of the triangle. So right now the situation is a little bit more complicated, because if you want to put the arrow from S to the triangle QRS, then actually, because of some topological assumption, we need to put also these additional arrows from S to RS or S to QS, and from the edges to the triangle. And in a moment, it will be clear why we have to do that. Because when you look at this topological space in terms of the partially ordered sets, so in short, posets, then we can represent the poset as a direct the topological space. We can represent as a partially ordered set, as a directed graph, where we have the vertices of the graph represents the cells of the simplicial complex, and they are ordered in layers by dimension. So in the top layer we have the 2 triangles. In the middle layer we have these 5 edges, and on the bottom layer we have 4 vertices. And the arrows going from top to down are the arrows which we can take from the boundary operator of the simplicial complex. So that's why we have the arrow from PQR to PQ and from PQ to P. Okay, and what we can do with the input data, with our original vectors from the input data. So when we take closer look, we can observe that in the middle picture we assume that from P we are going to the vertex to the edge PR. So let's put that information also on this partially ordered set. So from P we put an additional arrow going up from the vertex P to PR. The same for the other vertices Q, R, and a different situation is in the vertex S, because what happened here is that from vertex S we assume that the vector of the vector field is pointing into the triangle QRS. So let's mark this information on the poset. So this is this edge here, and how we can now interpret topologically this additional arrow from the middle picture. So in terms of topological information or set partially ordered set theory, it means that we need to take we need to make the set convex, the set SQRS. We need to make it convex, so it means that we need to add also the edges QS and RS. So what it means convex here? It means that whatever is between two vertices, so between S and QRS, it has to be also connected. And how right now we can interpret the graph? So when we look at these arrows up and down, we can observe that actually the arrows from the vertices to edges make very small oscillations. So from P, we can go to PR by the information given by the input data. And from the PR, we can go down to P by the information given by the topological space. And what happened in the more complicated situation in vertex S? From S, we can go to QRS by the information given from the vector field. And from QRS, we can go by the boundary operator to QS or RS. We can stay there. We can go back to QRS by the information taken from the input data and the criterion, the convexity criterion. Or we can go to vertex S to the bottom layer. We can stay there. Or we can go either to QS, RS, or the QRS. And these small oscillations, so the one on the right-hand side, or the one in between the vertices and the edges, give us a partition of the poset, or partition of the simplicial complex, partition into an object which we call a multivector. So if you know the Forman's theory of discrete vector fields, then you may notice that actually the vectors from Forman theory are the arrows from R to QR, from P to PR, or from Q to PQ. Those are just the arrows from Forman's theory. We extend this theory into more complicated objects, so we do not want to use only the singletons or doubletons from a theory, but we want to also have bigger subsets, like in the case of the QRS and vertex S. So in that particular case, the multivector is built from the vertex S, QS, RS the edges, and QRS the triangle. And formally, what we are doing here, we are just dividing the simplicial complex, the cells of the simplicial complex, into smaller set called multivectors. And the only assumption is that the multivectors have to be convex in terms of the partially ordered set. So that will be our building block of the whole theory. So let me show you one more thing, how we can interpret that kind of picture. So this is the same example. However, right now I splitted the picture into the multivectors. So we have the multivector P and PR here. We have the multivector S, QRS, and the edges here, and a multivector which is critical in terms of Forman theory and also in terms of our theory. The triangle does a singleton, so there is only the triangle as the multivector. And all the information which we have from the topological space or from the partially ordered set, we can encode it as this graph on the right-hand side. So V1 here is representing the vertex P and the edge PR, the multivector P, PR. So this is V1. V2 represents the second edge and vertex, V3 represents the vertex Q and edge PQ, V4 represents the triangle PQR, and V5 represents the multi-vector built here from the vertex S, the triangle, and the two edges. So we would like to analyze this kind of graphs. And what I would like you to remember from the slide is that we would like to analyze this kind of graph. However, the graphs, each vertex of the graph contains also some topological information. Namely, for each vertex, we have associated the subspace of the simplicial complex. Like for the V5, we have the subspace made from the triangle, the vertex, and the two edges. And please keep in mind that this information is there. But before that, before we can use that information, let me tell you what we would like to achieve from the analysis of the graphs. So first of all, some notation. So we'll speak about multi-vector fields. So this is the partition of a set of a cell complex into multi-vectors. So the multi-vectors are the convex set in terms of the order. We have the graphs. So GV is the graph from the previous slide, and we assume that we have some set of labels. So each vertex of the graph has a label, and our goal is to find a mapping from the set of labels into RD, where D is a fixed dimension of the space, the Euclidean space, and what we want, what kind of information we would like to have from this graph. We would like to say that whenever two labels have similar embeddings, similar values in this RD space, then there is some similarity in the local structure in the graph around those two multi-vectors U and V. And we would like to extend also this encoding into the whole graph, namely whenever two graphs are similar in terms of its dynamic, in terms of the multi-vector which generates the graph, we would like to have the mapping also close. And we extend the mapping into the whole graph just by mean of all the vertices of the graph and the embeddings of the vertices. And I will show you in a moment that actually this simple approach, by simple I mean taking the mean, is pretty good in that context. So in the next sections, I will tell you how we can compute that embedding phi. But before that, I would like to share you some information about our results, what we can achieve with such embeddings. So let's take a very simple example. Let's take a periodic orbit where the orbit is right now attracting, and there is a repelling point inside. So we have the vector field. The vector field is generated by the equations above. However, we do not know the equation for the whole computations. What we have is only the vector field. So this is our input data. And from the whole machinery, we can actually extract the periodicity. We can extract the repelling point in the middle. However, right now we'd like to also show how the embeddings may look like. So on the left-hand side, what I'm presenting is the embedding of the labels of the graph made from the multivectors, and the embedding is computed in 2 dimensions. So the mapping phi is going from the set of labels of the graph into the 2-dimensional Euclidean space. And what we can observe on that embedding is that actually there are 2 arms. One is colored in the rose color. One is colored in some kind of black, dark color. And I put a transparency whenever the points are closer to 0, 0. So whenever the points are in the ends of the arms, then the color is stronger. And with such embedding and such colors, we can right now put that information into the simplicial complex, which we have from the Delaunay triangulation, and we can color each simplex in the simplicial complex according to the colors of the embedding. And what we can notice here is that actually the encoding captures the periodicity. So this is the Rose arm of the embedding, and is able to capture the repelling point in the middle. This is the second arm of the embedding, and everything in between is more or less in the center of these embeddings. And because of the transparency put into the picture according to the norm of the points, you may notice that they are less important than the periodic orbit or the repelling point. Okay, so let's take something more complicated.
Mateus, do you mind going back? Can I ask a question?
Yes.
Of course.
So I really like the colorings, and you can visualize the the important parts of the dynamics. Can you explain the embedding again? So sort of how are you producing this embedding, or what intuitively is it measuring?
Yes, that's a good question, but I will go back in a moment to that.
Okay.
Because, in next slides, I will tell you in details how I can compute that embedding.
I see.
Right now, let me show you only the results, yeah. Because
fair. You got to give us the motivation first.
Yeah.
Hey, was your question similar, or did you have a different question?
Same question.
Okay.
Okay.
Cool.
Yeah. So please be patient. I will give the details in a moment. But before that, let me show yet another example. So right now we have two orbits and attracting point in the middle. So the equation is much more complicated. However, we do not know the equation. We just have the vector field. And right now, the computed embedding is in 3 dimensions. So 2 dimensions are not enough to distinguish those 3 features of the vector field. However, 3 dimensions are enough. And again, according to the coloring of the embeddings, so I just took the produced embedding and I give them colors according to RGB channels according to the 3 coordinates, and put the colors back into the simplicial complex. And what we can observe here is that again the orbit in the middle is very clearly visible. The critical point in the center is also visible, and the orbit, the attracting orbit outside is maybe not so easy visible. However, the colors are from the arms of the embedding. So there is this kind of green color which is here, and we may observe the green on this part and some kind of more yellow color on this part. Okay, so in that example, I took only one vector field. I produced the embedding, and I analyzed the space according to embedding. But let me do something more complicated. Namely, right now, I will go to an example where we have many vector fields, and the vector fields are generated in that particular case from simulations of prey-predator model, where the model is parameterized by those alpha, C, beta, delta, gamma, zeta parameters. And you like to analyze the model according to the changes of the alpha and C parameters. Of course, we can analyze the model also according to the changes of the beta, delta, and so on. However, to make things simpler, let me analyze the system according to alpha and C. And I'm taking the model from the paper cited here. And in the paper, we can find some analytical result which shows how the model behaves when we modify alpha and C parameter. So the authors claim that the alpha C space may be split into such 3 regions, where either there is oscillatory coexistence of 2 species, the yellow part, stable coexistence of this is the green part, or the predator win in the red part. So this result is analytical, and right now I would like to do or achieve something similar, just looking at the data. So what I'm doing now is I'm discretizing the alpha C space. So I have like something like 10,000 vector fields. So for each combination taken from the alpha C parameter space, I'm producing the vector field, and I'm running the machinery to analyze the vector fields. So on the top left picture, what we can see is the embedding of the vertices, of the labels of the vertices of each graph taken from the parameter space. This is maybe not so interesting in that particular case. What is more interesting is the embedding of the whole vector field of the whole graph. So on the right hand side, I'm plotting the embedding of each vector field. So right now, each dot here represents an alpha C combination, and the alpha C combination gives me the vector field simulated from the model. And now the colors are taken from the analytical results just to find some correlation of the embedding and the analytical result. So what we can observe here is that maybe there is no so clean, visible separation between yellow and green set. However, the barrier may be put somewhere here. The red set is more or less more separable. And what we see more is that actually maybe the dynamics in the green set, it's not so uniform. Maybe there is something different because the embedding is turning here. Yeah, so we have maybe something, the vector fields are similar in that area, but in that area they are much more similar to the red area. So maybe in the green set there should be some other kind of dynamics also distinguished. Okay, so that were two examples from simulation, and this is the last one example from simulation. Right now, I'm taking a simulation of fluid flow. So this is a model of wing, and we run airflow from left to right. And at each time frame of the simulation, we can get a vector field, velocity vector field of the airflow. And those are just three frames of the simulation. During the time, we modify the speed of the airflow, and we would like to observe the change of the airflow in the change of the embeddings of the vector fields. And on the bottom line, you may see not exactly the vector fields, but the stream plots produced from the vector fields, just to make things simpler to visualize. Okay, and what is going here for that kind of experiment? What we have on the axis is on the z-axis we have the time from 0 to something like 800 something, and on the xy coordinates we have the produced embedding, and according to the changes of time we plot each dot represents now the representation, the features of each time frame, and the colors represents the Reynolds number. So the Reynolds number, in some sense, describes the kind of turbulences in the flow. And what we observe is that at the beginning, when the flow is not yet stabilized, we just start the simulation. So there is maybe some kind of noise here. However, in a moment when we have quite large airflow, we have the simulation is turning in the feature space into left hand side. When we slow down, then we are going to the middle of the feature space, and we are turning to the right hand side. When we speed up again, then the situation reversed, and so on. So the picture shows that yes, the Reynolds number tells us something about the turbulences. However, it is not enough, because in the middle we can have either a high or low Reynolds number, and it cannot distinguish between high and speed, high and low airflow of the simulation. Okay, I'm going to skip this part. let me give you some details how we actually achieve the embedding and what we are doing. So just to remind what we want to achieve, we would like to achieve some extraction of graph features, either for vertices or for the whole graph. We would like to have fixed dimension D, and for the vertices or the whole graph, we would like to get D-dimensional feature vector, where the feature vector represents somehow the dynamics of the vector field. And there are many attempts to do that. So right now we are in the space of graphs, and there is many methods to extract some features of the graphs. You can just take degree of nodes, properties of the neighborhoods, some histograms of page ranks, eigenvectors, and so on. None of the method works for us, so we took something smarter. Namely, from 2014, we took a paper which describes a method called dblock. So the goal of the method is actually to take the adjacency matrix of the graph and to compress it, where each vertex right now, instead of be represented by the long vector of 0 and 1s, is represented by a quite small vector where the values are in the higher spectrum of values, like in floats or doubles. And the numbers of features for each vertex is much smaller than the total size of the graphs. And the D is fixed. So the goal of this thing is to find some anomaly in the graphs, some attributes prediction, clustering, ring prediction, and so on. And the authors has a very simple toy example for the method demonstrate this kind of graphs and its two-dimensional embedding. Let me skip that. You've already seen a lot of such embeddings. So what is the idea of the dblock method? The idea is to generate some random walks in the graph. So gamma is the number of random walks starting from each vertex, and the length of each walk is fixed, no bigger than t. And we pick up next vertex uniformly from the vertices, neighbors of the vertex. So just a reminder, we have the labels for each vertex. So right now, we will treat the labels as words in some artificial language, and each random walk will be a sentence in that artificial language. And having this set of random walks, we can generate a text document and use NLP methods to analyze this text document. So in that particular example, the text document will, in some sense, encode the structure of the graph as words, as sentences of the language. So there is some hypothesis from 50s that is called distributional hypothesis, that words that occur in the same context tend to have similar meaning. And the hypothesis is a starting point for a very large set of methods, which we can call word-to-vec technique. So there is a group of related models that are used to produce word embeddings. And the methods are based on some shallow two-layer neural networks. And the networks are trained to reconstruct linguistic context of words. The methods are very successful in terms of the natural languages. However, in our context, we'll use the same methods for our artificial language. So you can read a lot of very nice examples how the method works. For example, because the embeddings are in a vector space, then you can have also the arithmetic on the embeddings. And for example, the papers show such quite nice example. Then when we take the word Paris, the word France, and the word Italy, and we take the the embeddings and we do the arithmetic, then actually the nearest token is Rom. I'm not sure how accurate are the results. Maybe they are just fine-tuned for the papers. However, they show that there are many such nice examples taken from the embeddings. Okay, let me skip that. Here you can find some references. There are quite nice written papers with actually a lot citations in recent years. So if you are interested, then you can go to these papers. And let's go back to our problem. So how our workflow can look like. So let me remind that we have started from sampled vector fields. So this is our input data. For that sampled vector fields, we create the simplicial complex by the Delaunay triangulation. And on that triangulation, we create the multi-vector field. So we decompose the triangulation according to the vectors given in the data. Then we can transform the multi-vector field into a graph. Or when we have many multi-vector fields, then we can create many graphs. Or when we have just one vector field, then we create just one graph. And then we can find embedding of the vertices into RD. So we do that by building random walks. We have the artificial text corpus, and we build the language model using word-to-vec approach. Having that, we can embed either the vertices of the graphs, or we can embed a whole graph into RD. And whenever a new example of a vector field arrives, we can do exactly the same step. However, the model may be computed only on some training sets, and then we can use this word-to-vec model to find the embedding for the new data. There is one missing part in this workflow, namely, I haven't told you how we can assign labels to the vertices. On my toy examples, the vertices were just named V1, V2, and so on. And that kind of naming is not enough, yeah, because you can imagine that you can perturb the data a little bit, and then with that perturbation, the graph structure will locally modified. And right now, the enumeration of the labels of the vertices doesn't make sense. So we have to find another way of labeling, and the method of labeling has to be, in some sense, local, and it should be, in some sense, also how to say that intuitively. The method should be local, so it should take only some local information from the graph, from the vector field, and should be universal. So it means that whenever big or small the graph is, then the method should work also. And I'm going back to the thing which I asked you to remind from the toy example, namely, for each vertex of the graph, we have this small subspace of the simplicial complex. So V1, V2, V3 have the vertex and the edge, and V4 is only the triangle, and V5 is the vertex, two edges, and the triangle. So that are just some topological spaces, yes? some set of cells of the simplicial complex, and we can right now use them to actually produce the labels of the graph. How we can use them? So let me define the labeling at depth 0. So at depth 0, we just take the vertex, its local simplicial structure, and we put some properties of that simplicial structure as the label. So what kind of properties we can take? We can take, for example, the maximum dimension of the subspace elements. We can take the cardinality of the subspace. We can have the Euler characteristic of the subspace, and so on. Yeah, the information is there, and the information is local. It means that it's already attached to the vertex. For that particular two-dimensional example, we have a very limited number of such combinations. So the L0 values are like only few of such values you can have, and that's actually true even for much complicated two-dimensional cases. So to apply the word-to-vec technique, we need to have the labeling much richer. And how we can extend that simple idea to get richer labeling? What we can take, we can take the labels of the vertex itself, and we can take labels of neighbors of the vertex. And with the number of neighbors, we can go as a parameter d. So we can set some parameter d, which tell us how many neighbors we would like to take neighbors of the vertex v. How many of them we would like to take, and from that we can take. We can create additional tuple of values, and we can treat that tuple of values as label of the vertex, parameterized by the d parameter. And doing that, we have a much richer set of possible labels, and we can actually modify this parameter to get either lower or higher number of possible labels. And the truth is that actually for two-dimensional cases, the value of D4 is usually enough. In three-dimensional cases, the value of D like 1 is usually enough. So for the examples which I showed you, there were two-dimensional examples. I used value of D3 or 4 yeah, in that set. Okay, so that's all. I hope that I explained the method to you, and yeah, I'm open to some questions, comments. Thank you.
Thank you very much, Mateus. Before questions, let's unmute ourselves briefly and clap. Questions?
So I have a question. Hi, this is Bei. On page 30, like just the previous slide.
Yeah.
I'm a little bit confused by your definition of capital V1, V2, V3, V4, and V5. Those are the vertices in the graph?
So that are the vertices in the graph. However, the vertices are represented by the small subspaces of the complex. So V1 is representing the multivector PR. Yeah. So this is the multivector.
So
yeah.
So in your graph, V1, V2, V3, V4, V5 are vertices of the graph, but in your table, they are local neighborhood in some sense.
Yes, so V1 and V3 are local neighbors. So we have but V5 is not it's also a neighbor of V1, however, not direct neighbor. Yeah, because we need to travel at least between V5 to V3 and then to V1.
So what is a systematic rule? Like, I guess to make my question more concrete, what is the systematic rule of deciding the column 1 and column 2 of your table? Is that, you're saying that V1 in your table means the vertex P and edge PR. V2 is vertex R and edge QR, and V4 is just the triangle. So there's some rule of deriving this sub-network. What is the rule?
Yeah. So there is actually a lot of things to explain to tell you how we can actually create the partition from the data. This is out of the scope of this presentation. We already published a paper. I can send you a reference to that paper, where we described some greedy algorithm which takes the vector field, which creates the triangulation, and based on that creates the partition. That's very good question. Yeah, I skipped that topic here. I only told you that the method is in some sense based on the angle between the vector from the vector field and the edges of the triangulation. So more or less this is the criterion used there. And whenever the vector is close enough to the edge, then we map the starting point of the vector with the edge, or we are going from the starting point of the vector to the triangle, and we, because of the convexity criteria, we also add the edges in between. So yeah, there is a rule there. There is some non-trivial algorithm to do that, and yeah, it's not easy to do that in 2D and 3D in systematic way.
So since you mentioned that, sorry, this is a follow-up question. On the upper right corner, because this vector is sort of somewhere in the middle, it has a closest in a way to the nearby edge. So you kind of have essentially two projection. In the previous example, you have single projection because you just project it to the nearest edge. But in here, it's somewhere in the middle. But somewhere hidden in there, there must be some sort of threshold to say that if the angle to the nearest edge is above that threshold, I'm going to do a biprojection versus a single projection. Is that true?
Yeah, exactly. So the algorithm we published already, it uses a threshold, and actually the threshold is not enough to. Okay, so we can take the angle between the vector and the edges, and also we can take the angle between the vector and the barycentric barycenter of the triangle. Yeah, the segment which connects the starting point of the vector and the barycenter of the triangle. So right now we have 3 angles between the 2 edges and between the triangle, and according to the threshold, to some rules hidden in the algorithm, we decide where to put the connection in the graph. Yeah, it's there. And we also have yet another algorithm which is not published yet, which do not requires the thresholding. It's more like some optimization technique, but it's not published yet.
Okay, thanks.
Thank you for the questions.
Mateus, I had a question. So you have this sort of a collection of arrows, finite collection of arrows, and then you mesh the domain, and then you produce this multi-vector structure, which gives you the graph in blue, and then you do, things using the graph. I was curious if there's hope for results along the following line. So pick the same collection of vectors, but imagine changing the triangulation. So I don't know if you can really refine the triangulation because you can't really add more vertices, I suppose, without adding more vectors. But I don't know, maybe I change the triangulation. Do I expect the answers to be close in some sense? I mean, I know the answer is yes, but how much control do you think is possible to get along those lines?
So we do not have theoretical results about that, yeah, because one step further from that observation is that actually we can think what is the limit, yeah? If we put more and more points in the simulation and we refine the triangulation, then how accurate our results can be according to the ground truth of the system, yeah. So
yeah, that's maybe a better question than the one I asked. Yeah.
Yeah, but this is the same. The same theory has to be developed, yeah. When we also modify the triangulation, just put a very simple modification, how different the results can be. Right. Our observation from the simulation is that there is no such big difference. Yeah, we can actually usually when we do the experiment, we just take a dynamical system given by some differential equation, and you just randomly put points on the plane, and that's all. Yeah, and when we put more and more points, then we observe that there is no big difference between those kind of experiments. Of course, when the number of points is not big enough, then we may not observe the dynamics which is really there. But from some starting point, we observe that what we get is actually the graph truth. Yeah, so it means that the changing of the mesh is not so important. Yeah, we can take any kind of mesh in general. Yeah.
Thanks. That's interesting. Babe?
Since so I can take advantage of asking more questions. If I go back to the vocabulary, again in the same slides, is your final, you mentioned a labeling of the vertices in your graph, right? Mm-hmm. Is the label the last column?
Yes, also in that example, this is the label. It looks complicated, but it's just some kind of object in the computer memory. Yeah? In practice, what we are doing, we actually get a hash value of that object. Yeah. So in terms of programming, what you have here is just a tuple of 3 elements, and the first element is another tuple. The second element is a list of tuples, and the last element is another list of tuples. And like in Python or any high-level programming language, you can just take hashes of that kind of objects, and the hashes give you just single number, and that's enough to have the vocabulary as a number.
So if I understand it correctly, your L0 are the sort of labeling if I take no step. L1 are the labeling if I take 1 step.
Mm-hmm, yeah.
And I could technically do L2, L3, L4. So it depends on the length of the path I'm willing to take. Yeah. I'm going to get this thing. And then in practice, you said I need to choose a length, right? Do you choose 1 or do you choose 2? Like in practice, in the examples you show, how many steps do you take in terms of the labeling?
Yes. Yeah, so as I said, for the example, I used 3 and 4 as the value for D. And for 3-dimensional examples, is enough even to take 1, because the number of possible combinations of the multivectors which you can have, so the possible numbers of L0 values in 2-dimensional space, it's like, I don't remember, like several, only several numbers of such different kind of multivectors you can have. But when you go to higher dimension, in dimension 3, the structure is much richer. So it means that with L1, the number of possible labelings is quite rich, like several thousands, hundreds of thousands even. Yeah, depends on the example. But from the word-to-vec approaches, like the real natural languages, what we have, for example, in English vocabulary, we have like a few hundred thousands of different words. Yeah, so the goal is to, in some sense, mimic that kind of property of language. Yeah, to have rich enough structure of words, number of words, and then the context is the random walks do the rest in that.
But then the distance between those, once you embed it into, say, 3-dimensional space, and the distance is the added distance between the labels. What is the distance metric in that space?
So here we have the labels, and we use the word2vec to produce the embeddings of the labels. Mm-hmm. Yeah, word2vec, what it takes the vocabulary, the text document, and for each word in the vocabulary, it produces its embedding in RD. Yeah, so in some fixed dimensional space. I see. Okay. And this is done by the word2vec technique.
Okay, so ultimately it's a Euclidean distance once you have word2vec embedding. So it's in RD, so it's going to be Euclidean distance in RD.
Yeah, so usually people take Euclidean distance or cosine similarity, so it depends on the context, but those 2 distances are usually in use.
Okay, thanks.
Any further questions?
If there's no question, I can keep asking, but I want to give other people. So back to the very first example, I think it's on page 16.
Yes, this one?
Yes, so in here, if I go back, you kind of showed on the left picture, is that picture is a ground truth picture you obtained elsewhere?
So on the left, yeah?
Yeah.
So the vectors are just from the simulation, yeah? So we have the equation and we just plot the vectors. Right. And the ground truth is almost there. So depends what you mean by ground truth, because here we have finite information. Now is the question how we can represent the ground truth by the finite information. But actually, the ground truth, like when we are in the continuous space, is like here, yeah, that we have the two periodic orbits and the attracting point in the middle, and the method can extract that from the finite information also. So in some sense, this is ground truth, yeah.
Right. But I'm just saying, like the coloring of those simplices in the left picture by red and by green and by yellow, those were done through a different algorithm, right? This is sort of a baseline you want to compare against. And then the right-hand side is based on your embedding and clustering of the embedding and cluster them by points and then color parts of this.
Exactly.
Yeah. Okay. So somehow, you know, I really appreciate this word-to-vect framework of trying to encode this feature vector. But I'm curious because you kind of mentioned it on the fly to say that there may be, I'm wondering if there's simpler ways to encode this, right? I mean, somehow, because you're talking about red and walk and so on and so forth, like things to me that make sense in a graph are things like effective resistance and commute time. Those are also measurements that I can put on top of vertices. And I'm wondering, you know, whether they will achieve a similar results, or have you done that? Or you think that this word-to-vect is really the way to go because it's captured multi-level walk on this?
So yeah, I tried with different methods. Before I found the deep walk technique and the word-to-vect, I was trying to do something which is state of the art in the graph clustering and features extraction from graph. Like I mentioned, the PageRank approach, eigenvectors of graphs. I've tried many different things, and I wasn't able to extract that kind of results. However, maybe I wasn't trying hard enough. Yeah, maybe there is something simpler, but I couldn't find that. Yeah, so definitely I was trying different approaches, but without success. Yeah, and this approach was the first one which gave me much better results than the previous examples.
And I see. So okay.
Yeah, and the way how I validated that was that actually I started the whole work in some classification problem when I have on the input as a input data, I have bunch of vector fields, and the goal was to classify the vector fields. And during that time, the vector fields were quite complicated. That were actually the one from the observation of the magnetic field of the sun, and the state-of-the-art approaches were just very poor, yeah, in terms of the classification score. And the one with this word-to-vect and deep walk were much better. And for example, let me show you something which I skipped, yeah, because here what you can see is that actually there is this periodic orbit green and yellow and the attracting point. Yeah, so in terms of the dynamics, in terms of dynamical systems, the information is there. Yeah, like the information which is contained in this vector field. Yeah, so we know that there is the periodic orbit, first and second, and the attracting point. However, we may have a kind of vector fields which doesn't have any critical point, any periodicity, and so on. So let me show you the example which I skipped. Namely, okay, I do not want to go into the details. However, what we are working on right now is a method which can create from a time series. So we have the standard time series. From that, we can create a vector field, and now we can think how we can classify the time series based on the embeddings of the vector fields. Yeah. So this tiny example, which is just time series taken from parabol. This is the vector field which which is generated from the parabol, and this is the scheme plot of the vector field. Let me skip the details. However, what you can observe here on that vector field is that there is no critical point, there is no periodic orbit. There are just straight flows in the trajectories. And when you take the whole database of such time series, then we have 6 classes like here that are just the representatives of the classes of the time series, and they associated vector fields, and none of them has any critical point or periodic orbit. They are just direct flow, and the flow may be complicated in some sense. Yeah, like here we have quite smooth trajectories, but here we have quite complicated trajectories. And now the method works also. So this is the embedding and the separation between the classes of the vector fields. So in that sense, when we take for that kind of vector fields, when we take the methods which are based on anything like periodicity, so like PageRank is in some sense based on some attracting points and so on, or the eigenvalues of a graph also are based on these attracting vertices. So we do not have attracting points there. Yeah, there is no attractor. However, the method which we use here is able to, in some sense, separate the classes of the vector fields. So I hope that it fulfills the answer to that question.
Yes, great, thank you.
Thank you very much. So before I end the recording, let me just say thanks again, Mateus, for a very beautiful talk.